Thank you. I'm Daniel from TU Delft in the Netherlands, and I will discuss our paper, Language-Parametric Reference Synthesis. So, we are going very quick through this. So what's the problem we're trying to solve? We perform refactorings to our code all the time. This is to improve its maintenance or just to improve the maintainability, well, to improve the maintainability, to improve the structure of the program. And the kind of refactorings that we do is to move code around or to rename variables and these kind of things. And often IDEs have automated refactorings that can help us do these things. That's great. But one aspect of refactorings that we would really like is that they preserve the behavior of the program. After the refactoring, the program should still do exactly the same as it did before. And in particular, it should preserve the name binding structure of the program. So if you have a variable x, like in the example on the left, that resolves to the x at the top of the file in class A or module A, then after the refactoring, where we move module C lexically in module B, the x should still resolve to that same x at the top of module A, but now instead it resolves to the closer x in module B. This changed the behavior of the program and the value has changed as a result. The correct refactoring would be to also change the reference here. So it should instead, in this example, be a.x. This would be the correct name binding, and we want this property in our refactorings. And we have a solution for this. It's called reference synthesis. Our approach, we use it as a building block to implement refactorings. So when you're implementing a DSL or another small language, just the added effort of preserving name binding is a lot already. So our approach is 3 steps. First, we lock the references in the original program. For every reference in the original program, we determine what declaration in the program it resolves to before the refactoring. We remember this, and then we perform the transformation. We move code around, we rename variables, and after this, we synthesize references. We take those locked references, and we find a concrete reference, concrete syntax in the language of the program that resolves again to the intended declaration. And here's an example. The same example program. We take our x before a reference to x in the print line before the refactoring. We lock it, saying, well, actually, it refers to x1 at the top of the file. I've added numbers to distinguish the different occurrences of x, but they are not in the syntax. Then we perform the transformation. We move the module lexically inside, move module C lexically inside module B, but we keep our locked reference just the way it is, saying that it resolves to x1. Now comes the magic part. We synthesize the reference. We take this locked reference and we find a concrete syntax that corresponds to it that will again resolve to the intended x variable at the top of the file, in this case a.x. And we do this using the static semantic specification of the language, which means that we can do it in a language-parametric way. So not just for a specific language, but for any language for which you give us a static semantic specification, we can synthesize these references. Why do we do it in a language-parametric way? It will help you when you're building your own language, because for those languages you probably already want to write the specification anyway, and then you already have this building block for implementing your refactorings. So how does it work under the hood? We use, in this approach, the type checker. We use the statics meta-language of the Spoofix language workbench, which is a language where you use constraints to specify the typing constraints of your language. You specify things like the type of an expression is an integer, but you also use it to specify the name binding structure of your program. It comes with a constraint solver to solve these constraints on a particular input program. If all the constraints are solved, well, your program is typed correct. If the constraints derive false, well, clearly you have a type error in your program. And it's also possible, in some rare cases, that the solver cannot really solve all the constraints yet, and it needs some more information. This typically doesn't occur in a normal programming language, but we will use this ability of the solver to get stuck to our advantage. So in our approach, we extended this solver with the ability to expand constraints. The idea is if we have a constraint and we make it such that the solver will get stuck on this constraint, then we intervene and we try different alternatives for completing this constraint, and this will allow us to find the reference that we need. I will show step by step how this works. We need several ingredients. Well, we need the static semantic specification of the language, shown here on the left. It is a set of premises and conclusions, a set of rules. So, for example, the top rule says that the type of a plus expression is integer if and only if the type of its sub-expressions are also integer. But there are also constraints, like the one in tdef, that say something about the name binding structure of the program. This constraint says, for example, that from a scope in your program, you should be able to resolve to a reference with a particular name. How does this work? The program, shown in the middle, is represented by a scope graph. That's representing the name binding and scoping structure of the program. So, for example, module A, module B, and module C are all represented as a node in this graph named as A, as B, and as C, respectively. And also the definitions x1, x2, and the function foo are represented as nodes in this graph. If two scopes are lexically nested inside each other, there's an edge between them that says lex. If there's a scope that you can reach from another scope through a particular name, then there's another edge, for example, mod or def. This represents the name binding structure and the scope graph of the program. So if we need to resolve a variable x in the program, say from the print line statement, we are in the scope of sfoo on the bottom right. Now we try to find a path in the scope graph that brings us to some declaration that has the name x. If we find such a path, we've resolved the name. If we don't find such a path, well, it's an unresolved reference. And this path has to conform to a certain regular expression of the edges that it can traverse. For example, you might look for your variable x in lexically outer scopes, but you might not want to traverse to a completely different class without actually naming this class. So we take our program with the locked reference, remembering that it resolves to, or that it was locked to x1, and we replace this locked reference by a hole, a free unification variable. And by doing this, when we allow the constraint solver to use its static semantic specification on it, it will try to solve as many constraints as possible, and it will be left with some constraints that it just cannot solve. In this example, it is left with a constraint that says, well, the type of this expression, which is this free unification variable, should be integer. But the expression is, well, a free unification variable, so the solver gets stuck here. It stops solving. It didn't determine if the program is type incorrect. Also, it is not type correct. It just stops here. And at the same time, we're tracking that this free unification variable h corresponds to a hole and what we have synthesized for this hole. In this case, we have not synthesized anything yet, so question mark h still maps to question mark h. We take the typing rules of the program, and this is where our work comes in. We see what conclusions of these typing rules we could fill in the place of this stuck constraint. In this example, we have three typing rules that we could apply. The first one assumes there's an addition. The second one assumes there is a simple reference named x. And the third one is a qualified reference, some m.x. So we will try to insert each of these alternatives as an extra constraint. So we now end up in three different states. In one state, we assume it's an addition. In the next, it's just a simple reference. In the third, it's a qualified reference. And for each of these states, we've added these constraints. And we've updated the mapping of the holes to the syntax. We will let the solver solve these. It will try to solve as much as possible, again, using the static semantic specification of the program. For the top example, it solved so much that it now concludes that, well, it's an addition, but I still don't know the expression on the left or right-hand side, so it got stuck again. For the middle one, where it is some simple name x, but x is also not named, it's an unknown name, the unsolved constraint is a so-called query constraint that will be used on the scope graph to find the declaration that we're resolving to, but since the name is unknown, it cannot solve this query yet. And the bottom one with the qualified name has both the query constraint left over and a constraint on the qualifier itself, saying that there must be some qualifier that it also doesn't know yet. Let's continue with the bottom two examples. We'll now expand the queries. We know what declaration this reference should resolve to. We know its name in the program, so we can actually fill in this query with the name that we expect it to be. So we do this for the middle example, and we fill in X, and basically saying, well, this whole is actually the syntax just X, reference X. And for the bottom example, there's two X's that we can fill in because there's two declarations that are named X that we can reach, and we try both of them. We again invoke the solver. Well, for the top constraint where we just filled in X, actually the solver concludes that it is not satisfiable. Well, actually we conclude it's not satisfiable. The solver is happily solving this constraint, this query constraint. It resolves to a declaration X, but it resolves actually to SX2 in the scope graph, which is for X2 in the program. And we actually intended it to resolve to X1. So the first alternative we can discard. Just writing X is not going to bring us to the declaration that we intended. For the second and third, well, the query is also solved, and we get the two residual constraints. The difference between these two is that in the top one, it assumes that there is some scope SA, where the qualifier brings us to, in the scope graph, and for the bottom one, it's some scope SB. Both have an X declaration X in them, in the scope graph. So we come in again, and we expand on those constraints once more. So for the scope of mod rule, predicate, there's several rules that we can try. Again, the top one, which is just a simple name, or the bottom one, which is again a qualified name. We can, of course, repeat this as much as we want, adding qualifiers as much as we want. Well, we'll try to converge as quickly as possible to the shortest solution, because that we know will resolve to the intended declaration. Doing both of these alternatives to both of the inputs gives us 4 new states, where we basically create each combination of these rules and the predicates that we're expanding. Again, we invoke the solver. The solver leaves us again with a whole bunch of constraints, some query constraints and some predicate constraints. And again, for the unsolved query constraints, we can insert, well, actually, we know the name of the declaration that corresponds to SA or SB. So we'll just insert those. So for the top example, we get A.X followed by B.X, and for the bottom example, it's the same. However, if you look at the constraints, you will see that some of the scopes are actually different, so some of these will actually not unify correctly. So we invoke the solver once more, and now finally it can make some conclusions. For the top example, it actually solves all the constraints. And it concludes, well, actually the syntax for this whole that has to resolve to X1 is A.X. For the second one, actually the constraint that SA matches the target of where our qualifier resolved to is actually not satisfiable, and that's the same for the third state. And for the fourth state, it is satisfiable, but we conclude it's not resolving to the intended declaration, so we discard it. And this way, we have been able to synthesize the syntax for the whole that we were looking for. We now have a reference to the X in module A, despite us having moved some code around and changed the whole name binding structure of the program. There are some additional challenges here. Of course, performance. There's a huge search space that we can try, but we try to converge quickly to a solution by firstly only expanding the relevant constraints. Furthermore, expanding the oldest constraints, because those are probably the ones that have the biggest impact on the program. We try to expand query constraints, because those are the ones where we can insert actually the name of the thing we're looking for. And then we expand predicate constraints that yield queries, because the quicker we go to a query when we're looking for a reference, the more it makes sense. And additionally, there's a problem where solutions to one whole can depend on solutions for another whole. For example, here, if there's also a whole for the import, the print line X we cannot easily solve because it could resolve through the import, so we have to resolve the whole for the import first. We evaluated our approach. We've shown that it's sound, and it's sound by construction, and we have more than 2,500 test cases of 3 small languages of which we had already an existing specification in statics on which we applied our approach. We were able to solve for most of them all the holes within 60 seconds, and basically for every hole, except for some outliers, every hole we could solve in 1 second. So thank you for listening. Find also our paper for more details, and if you have any questions.
Let's thank the speaker.